A modern cargo ship operates continuously during its voyage across the ocean. The ship requires electricity for lighting, for pumps, for refrigeration, for navigation systems, for communication systems, and for hundreds of other systems. The electricity requirement is enormous. A large container ship might consume as much electricity as a small town. Ankak Jemi Basiche Bur Electric Prizine to kilowatts. The ship is miles from land, operating in the middle of the ocean. The ship must generate all its own electricity. The ship must be an independent electrical power plant. Gemalaran Nassal Electric Uratigini Anlamak, Electric Mahendasligi, Energy Uratimi, Energy Yonetimi Ve Modern Gemalaran Denizd Bagamsiz Alarik Kalasmasini Saglayan Karmasik Systemlaran Principalrini Ortaya Koymaktadir. Today we're exploring how ships generate the electricity they need to operate continuously during their voyages. The primary method of generating electricity on ships is using diesel generators. A diesel generator is essentially a diesel engine coupled to an electrical generator. The engine burns diesel fuel and converts the chemical energy into mechanical energy. The mechanical energy drives the electrical generator, which converts the mechanical energy into electrical energy. The electrical generator produces alternating current at a specific voltage and frequency. The voltage is typically 400 volts or 6,600 volts. The frequency is typically 50 or 60 hertz. Multiple generators operate simultaneously to produce the total electrical power required by the ship. The number of generators on a ship varies depending on ship size and power requirements. A small ship might have 2 generators. A large container ship might have 3 or 4 generators. Each generator might produce 1,000 kilowatts or more. The total electrical capacity might be 3,000 to 4,000 kilowatts or more. This is enormous electrical power. The generators must be sized so that if one generator fails, the remaining generators can still power essential systems. This redundancy ensures that the ship remains operational even if a generator fails. The diesel engines that power the generators are similar to the main propulsion engine but much smaller. These auxiliary diesel engines typically produce 500 to 2,000 kilowatts per engine. The engines operate at a constant speed to maintain constant frequency of the generated electricity. The speed is typically 1,200 or 1,500 rpm to produce 50 or 60 Hz frequency. The constant speed operation is important because the electrical frequency must be stable for sensitive electrical equipment to function correctly. The generators themselves are sophisticated electrical machines. A diesel generator contains a rotor that spins inside a stator. The rotating magnetic field from the rotor induces electrical current in the stator windings. The induced current is the electrical output. The generator must produce the correct voltage and frequency. The voltage is regulated by controlling the magnetic field strength. If the voltage becomes too high or too low, voltage regulators adjust the magnetic field to bring the voltage back to the correct level. If the frequency becomes too high or too low, the engine governor adjusts the engine speed to bring the frequency back to the correct level. The electrical load on the ship varies throughout the day. During the day, when more lighting is needed and more systems are operating, the electrical demand is higher. During the night, when less lighting is needed, the electrical demand is lower. The generators must be able to handle varying electrical loads. If the electrical load suddenly increases, the generators must provide additional power. If the electrical load suddenly decreases, the generators must provide less power. The load management systems automatically adjust the number of generators in operation to match the required power. If only a small load is required, one generator might be sufficient. If a large load is required, all generators might be operating. The fuel supply system provides diesel fuel to the generators. The fuel is stored in large fuel tanks in the ship's lower sections. The fuel is pumped to the generators through a fuel system that includes filters and pressure regulators. The fuel must be heated to the correct temperature and viscosity before it enters the engine. The fuel consumption of the generators varies depending on the electrical load. A typical large ship might consume 5,000 to 10,000 gallons of fuel per day from the generators alone, in addition to the fuel consumed by the main propulsion engine. The cooling system removes the heat generated by the generators. The diesel engines that power the generators produce heat, just like the main propulsion engine. Cooling water circulates through the engines to absorb the heat. The hot water then passes through a heat exchanger where it transfers the heat to seawater drawn from outside the ship. The cooling system must be sized to remove all the heat generated by the generators operating at full capacity. If the cooling system fails, the generators will overheat and be damaged. The electrical switchboard is the control center for the ship's electrical system. The switchboard contains circuit breakers, switches, and monitoring equipment. The switchboard shows the voltage and current from each generator. The switchboard shows the total electrical load. Operators monitor the switchboard to ensure that the electrical system is operating correctly. Alarms alert the operators if any parameter is abnormal. The operators can start and stop generators as needed to match the electrical load. The switchboard also contains protection equipment that automatically shuts down a generator if a fault develops. The electrical distribution system carries power from the generators to all the ship's systems. The main distribution lines carry power at 400 volts or 6,600 volts. Step-down transformers reduce the voltage for use by different systems. Some systems require 400 volts. Some systems require 230 volts. Some systems require 24 volts for control circuits. The electrical distribution system includes circuit breakers and fuses to protect the systems from electrical faults. If a short circuit develops in a system, the circuit breaker automatically disconnects that system to prevent damage to the entire electrical system. Emergency power systems provide electricity in case of failure of the main generators. Most ships have a backup generator dedicated to emergency power. The emergency generator is smaller than the main generators but can provide sufficient power for essential systems. The emergency generator operates automatically if the main power system fails. The emergency power system might power navigation lights, emergency lighting, radio systems, and other essential systems. The backup generator helps ensure that the ship can navigate safely even if the main generators fail. Uninterruptible power supplies provide instant power for critical systems that cannot tolerate any interruption in power supply. Navigation and communication systems are particularly sensitive. An uninterruptible power supply contains a battery that stores electrical energy. If the main power fails, the battery instantly provides power to the critical systems. This prevents the loss of navigation data or communication signals. The battery in the uninterruptible power supply is continuously charged by the main electrical system. If the main power is interrupted, the battery provides power while the backup generator starts up. Alternative power sources are being explored for future ships. Solar panels installed on the ship can generate electricity during the day. The solar power can supplement the diesel generators, reducing fuel consumption. Wind turbines might be installed on some ships to harness wind energy. However, the electrical power from solar and wind is intermittent and cannot completely replace the diesel generators. The diesel generators provide reliable power regardless of weather conditions. Therefore, diesel generators will likely remain the primary power source for ships for the foreseeable future. Future ships might use fuel cells to generate electricity. A fuel cell combines hydrogen with oxygen to produce electricity, water, and heat. Fuel cell technology is being developed but is not yet widely deployed on ships. The primary challenge is obtaining sufficient hydrogen fuel and storing it safely on the ship. As fuel cell technology matures, fuel cells might become an alternative power source for ships. Liquefied natural gas engines are also being deployed on some newer ships to power both the main engine and the electrical generators. These engines produce less pollution than traditional diesel engines. Battery storage systems might become more important on future ships. Batteries can store electrical energy generated during periods of low demand and release that energy during periods of high demand. Batteries can also smooth out fluctuations in power generated by renewable energy sources like solar and wind. However, current battery technology cannot store the enormous amounts of electrical energy required for a large ship to operate for days between port calls. Significant advances in battery technology would be required for batteries to become the primary energy storage medium on ships. The electrical systems on modern ships are increasingly automated and monitored by computer systems. Sensors throughout the electrical system continuously measure voltage, current, and other parameters. Computer systems analyze this data and automatically adjust the electrical system to maintain optimal operation. Alarms automatically alert the crew if any parameter deviates from normal. Remote monitoring systems might eventually allow shore-based technicians to monitor the ship's electrical system in real time and provide guidance to the crew for troubleshooting and maintenance. The engineering crew on a ship includes electricians and electrical engineers who maintain and monitor the electrical systems. These professionals must understand the complex electrical systems and be able to diagnose and repair electrical problems while the ship is at sea. The training of qualified electrical personnel is essential for ensuring that the ship's electrical systems operate reliably. Regular maintenance of generators, cooling systems, and electrical distribution equipment is necessary to prevent unexpected failures. Understanding how ships generate electricity reveals the remarkable self-sufficiency of modern ships. A ship is essentially an isolated electrical power plant operating in the middle of the ocean. The generators must provide reliable power for all the ship's systems. The electrical systems must include redundancy to ensure continued operation even if equipment fails. The management of electrical power is complex and requires sophisticated equipment and trained personnel. The result is that ships can operate reliably far from land, generating all their own electricity and maintaining all their own systems. If you're fascinated by how ships operate as independent power plants generating all their own electricity, and how electrical systems ensure reliability through redundancy and sophisticated control, subscribe to the channel. We regularly explore how engineering systems ensure reliability under challenging conditions. Understanding ship electrical systems reveals principles of power generation, load management, and system design that apply far beyond maritime operations. Your subscription supports the creation of content that explores how complex technical systems enable human achievement. Thank you for watching and for your interest in understanding how ships generate electricity while at sea.